I want to welcome you to another one of our video lecture series, and in this series we will be looking at the design of uh, let's say design of a footing with strap beam. And before going into the details regarding the design of a footing with strap beam, we will discuss some basic concepts and design of combined footing in our first video lecture today. And in our next video lecture, from next video lecture onwards, we will look at the design of a combined footing. Not you can say combined footing, or basically we will look at the design of a footing with strap beam, both in Excel sheet and then in CSI safe software also. So we will be looking at the design portion in our upcoming videos. Today we will start with basic concept and design of combined footing. So we have looked at the design of isolated footing in one of our video lecture series. If you go to our YouTube channel Inquisitive Engineer and search for design of isolated footing, there you can find a video in which we discuss on design of isolated footing in Excel sheet, that is manually. And we also discussed about the design of mat foundation through the use of safe software in one of our lecture series also. You can search for that particular video. I will also post the link of those two videos below this video in YouTube, or you can search in YouTube by yourself. So we have looked at the design of isolated footing and mat foundation, and today we will look at the design of combined footing. And in design of combined footing, we will look at some basic concepts today, and the reference book that I have used is the Reinforced Concrete Design book by Pillai and Menon. So I want to acknowledge my reference at the beginning. So let's start with today's lecture. So basically, a footing supporting more than a single column or wall is called a combined footing. Generally, in residential buildings of lesser heights, what we do is we design a single footing for a single column, and that footing is designed to withstand all the loads coming onto that footing from the column that the footing is supporting. But if our footing is supporting more than a single column or more than a single wall, then we call that a combined footing. Multiple column foundations become necessary in soils having very low bearing capacities. For example, if this is our combined footing slab, then it can support either 2 columns or even more than 2 columns also, 3, 4, 5 columns. And such multiple column foundations is necessary when the soil, that is, when the soil on which this footing is resting has very low safe bearing capacity. So combined footings become necessary even in soils having moderate or high safe bearing capacity when columns are so closely spaced that isolated footings cannot be conveniently provided, and an exterior column located along the periphery of the building is so close to the property line that an isolated footing cannot be symmetrically placed without extending beyond the property line. That means there are two conditions in which we use combined footing. The first condition is when the soil has very low bearing capacity, and the second condition arises even when the soil have moderate or high safe bearing capacity. And what happens in those conditions is that even if the soil has moderate to high safe bearing capacity, combined footings become necessary in two conditions. So first condition is that our architectural plan is such that two columns are spaced very closely apart, such that whenever we provide isolated footing for these two columns, then the footing slab of these two columns tend to overlap. So in such cases, for example, if these are our two columns and if we have designed, okay, so if these are our two columns which are spaced very closely apart, and if we design isolated footing for these two columns, let's suppose that these isolated footing slabs for these two columns intersect in this shaded area. So in this case, even when our soil have sufficient bearing capacity, then we have to provide combined footing. One is this case, and the second case is that whenever our architectural plan is such that the columns are located along the property line. That means, for example, if you suppose that this is our site plan, and according to our architectural plan, our building is to be located here. So this is the position for our building, and you can see that this edge of the building is located along the periphery line. So what happens is that it may not be possible along this property line to provide a symmetrical isolated footing. In such case, if this is the property line, then you may have to build your columns at the periphery, that is eccentric along one of the x or y axis. So whenever our building plan is such that it is located along the property line, or one of the grid lines of our building overlaps along the property line, then in that case we may not be able to symmetrically place isolated footing, and in that case also we may have to design combined footing. So remember, when one of the columns is very close to the property line, an eccentric footing can be designed only when the load acting on the edge column is small. We can design these eccentric footings and thus design an isolated footing, but this becomes possible only when this column has a very less amount of load coming onto this. So what will be a better alternative? A better alternative will be to combine the footing of this edge column with that of another column in the same line, that is either along this x-axis or along this y-axis. So in this case also we can, or we may have to design a combined footing. And another thing is that the strip and mat foundations. Strip foundation means like this combined footing, and mat foundation, we can also assume mat foundation as a combination of various combined footing. What happens is that the strip and mat foundations, because of their continuity and rigidity, they reduce the differential settlement of individual columns relative to each other. So because when we find some local variations in the quality of the soil, that may cause differential settlement. In that case also we prefer combined footing. And further, if we go further from that case, if the safe bearing capacity of the soil is so low that even raft foundation cannot be supported, then in that case we may have to go for a deep foundation such as piles. So these are few conditions for design and construction of combined footing. One is that the soil has very low safe bearing capacity. There are local variations among the soil that may cause the differential settlement of different foundations. And another case, even if there is sufficient safe bearing capacity, then the columns may be spaced so that the isolated footing slabs tend to overlap, or our building is located along the property line. In that case, we may have to design combined footing. So let's talk about the geometry of two column footings first. So there is a figure you can see on your screen right now. So how do we select the geometry of two column footings? Always remember that the geometry of the footing base should preferably be selected so as to ensure that the centroid of the footing area coincides with the resultant of the column loads. And these column loads may include any moments, if there are any moments also. So our footing dimension is always selected in such a way that the centroid of these loads coming from the columns, there may be more than two columns also, but in this figure, if you see here, the centroid of the loads coming onto these columns should coincide with the resultant or the centroid of the footing area. So what happens if we ensure coincidence between the resultant of our column loads and the centroid of our footing area, then that will result in a uniform distribution of swell pressure, and that uniform distribution of swell pressure is desirable because it helps in avoiding the tilting of the footing. So this is the first step in selecting the geometry of our footings. to coincide the resultant of these column loads with the centroid of our area. So let's look at diagram. You can see that S is the center to center spacing between these two columns. P1 is the load coming onto this first column. P2 is the load coming onto this second column. R is the resultant of these two loads. A is the distance from the property line. That means this edge of our slab to the center of the edge column. To the center of this edge column. And okay, these are our notations here. And let's see here. When the exterior column, which has the space limitation for an independent footing, that means this column. When the exterior column carries a higher load, a rectangular footing or a trapezoidal footing with a reduced width under the exterior column may be provided. Let's see here. This is our exterior column. So if this exterior column carries a lighter load, that means lesser load as compared to this inside column, then we have two options. We can either design a rectangular footing like this of dimensions L and B, or we can design a trapezoidal footing in which the area under this column, that means the area under the column carrying the lighter load, is lesser as compared to the area of the column carrying a heavier load. So we have two options. Either we design a rectangular footing or a trapezoidal footing. Similarly, if the exterior column carries the heavier load, like in figure E, then we can design a trapezoidal footing such that the area under the column carrying the heavier load, that means this column carrying load P1, is higher. If you see here, the area under this column P1 is higher as compared to the column carrying the load P2. So this is how we select the geometry of our combined footing. And you can see here, you can also understand this through the concept of statics here. The resultant is acting at a distance x bar, and this x bar distance will be greater than or equal to s by 2 when the exterior column is carrying lighter load, because all the loads are concentrated, or you can say most of the load is concentrated onto this inside column. So the resultant also will be nearer to the inside column, such that the distance between this exterior column to the distance of this resultant will be greater than the half of this distance, s by 2. Similarly, if the exterior column carries the heavier load, then x bar, that means the distance of resultant from this column, this exterior column, this x bar will be less than s by 2. The resultant will act nearer to the S column. So this is how you select the geometry of two column combined footing. Remember that combined footing may have or may support more than two columns also, but we will generally talk about two column combined footing in this presentation. And finally, once you have selected the geometry of your combined footing, now it's time to fix the plan dimensions of your footing. So let's look at the plan dimensions of the two column combined footing may be selected to satisfy the following two requirements. One requirement we have already discussed, that the resultant of the column loads must coincide with the centroid of the footing, which is written here in second point. The line of action of the resultant of the column loads must pass through the centroid of the footing. And we can select, finally, we can select the base area of the footing as total service load divided by allowable swell pressure QA. So this is how you select the base area of the footing. Now we have the value of base area. Now after selecting the base area, now we have to select the length and breadth. So what we can do is, in the case of rectangular footing, the second requirement results in a length L of the footing equal to 2 times x bar plus A. The edge distance A may be fixed with reference to a property line, otherwise it may be suitably assumed. If you look at our previous slide, x bar is the distance from the edge column to the resultant of the column loads, and A is the distance from this property line to the center of our edge column. So In order to ensure that the resultant of these two loads pass through the centroid of our footing, we have to assume the length of our footing equal to 2 times x bar plus a. And after finding this length, which is 2 times x bar plus a, you can find the width of the footing is a over L. This is the case for rectangular footing. First find the base area, then find the length, and then find the breadth. But in the case of trapezoidal footing, what we do is usually the length L is selected first and the dimensions B1 and B2 adjusted to satisfy the two requirements cited above. So this is a very theoretical part. If you go through some books for design of reinforced concrete structure, and in that book if you search for the design of combined footing section, then in those concrete books you can generally find the formula for fixing the length and breadth of different types of rectangular or trapezoidal footings. I'm only discussing theoretically here. First I have discussed about the rectangular footing, then I discussed about the trapezoidal footing. If you consult any standard textbook on design of reinforced concrete structures, then in that book there will be directly given formulas for calculating all this length, breadth, or in case of trapezoidal footing these two B1 and B2, because the width is not same for trapezoidal footing. One is B1 and another is B2. You can find the formula for all of these symbols or all of these parameters in any RCC design book. So I have not talked about those formula here. I have only talked about the methods to fix the plan dimensions, that is length and breadth. So first you selected the geometry of the footing and then you fix the plan dimensions. Now let's look at some load transfer mechanism. Now the drawing is the same here. We have one ace column and we have one column at the center. Although this is ace column, remember that here is no eccentric footing. The column is still located at the center of this footing slab. So we have just designed a simple combined footing and we have not designed for any strap beam here. So the factored net swell pressure Qu is computed as the resultant factored load divided by the base area provided. Factored load we get from this, we have already Pu1 and Pu2 here. We can get the resultant factored load from this Pu1 and Pu2. We have selected the base area in our previous slide as A. So by using this factored resultant of factored load and the base area, we can find the factored net swell pressure. And this pressure is assumed to act uniformly, or this pressure is assumed to be distributed uniformly and acting on our footing slab. Let's look here. I will show you one diagram before proceeding further. So you can see here, this is a somewhat 3D diagram regarding a combined footing with two columns. You can see at the bottom these arrows. This is the uniform swell pressure acting on our footing slab. And this factored uniform swell pressure is represented by Qu, and this pressure is we get is Qu is equal to the resultant of factored load divided by the base area that we selected. And this Qu is assumed to act uniformly, and this acts as a uniform swell pressure. So the base slab of the combined footing is subject to two-way bending and one-way as well as two-way shear. A simplified load transfer mechanism may be assumed. The footing is treated as a uniformly loaded wide longitudinal beam, factored load QUB per unit length, supported on two column strips, which in turn act as transverse beams cantilevered from the columns. Let's go to that diagram again. So our factored uniform swell pressure is Qu, and if you multiply Qu by the width of our footing B, then we get the uniform load acting as a swell pressure per unit length on our footing slab. So what happens in that generally the width of our footing, which is B, is lesser than the length L. In case of a combined footing, this width of our footing B is very much less compared to our length L. So that means what we can assume is that the flexural behavior is predominantly one way. That is, we assume that this combined footing bends in the longitudinal direction. You can see here, this is a section of this combined footing along the length. We have got a section here in the middle, and this is our QU swell pressure acting on this longitudinal section, and along this section along another plane, this is swell pressure acting along the another plane. So because of the fact that the length is very much greater compared to the breadth, we can assume that the bending of our combined footing is primarily in the longitudinal direction. So the primary action that is acting on our combined footing is one-way bending and two-way shear. We have to check and design for both one-way and two-way shear, but primarily we have to design for the flexure behavior only in the longitudinal direction. The two-way bending or two-way action for flexure may be limited, but that transverse bending is limited only along these column strips, so that is not much greater. We have provided here some transverse steel. If you can see on this diagram on the right hand side at the top, this transverse steel is limited to this area under the column strip. There are a few bars only, as you can see, because we assume that the transverse bending is only limited along these column strips here. But longitudinal steel we will provide throughout this slab because the longitudinal bending is predominant, and we have to design for this longitudinal bending in our two-way slab. So you can see here these width of our column strips, C2 plus 0.75D and C1 plus 1.5D. The C2 and C1 are the dimensions of our column, and D is the effective depth of our footing slab here. This width means we assume that only along this width the transverse bending is important. So only along this width we provide the transverse steel as shown in our diagram here, but longitudinal steel is provided along the whole length of our combined slab or combined footing. So let's move forward here. In this load transfer mechanism, the thickness of the footing is usually governed by shear consideration. Remember this. The critical section for one-way shear. We discussed critical section for one-way and two-way shear, and also for bending moment in the design of our isolated footing also. The critical section for one-way shear are at a distance d from the column face and at d by 2 from each column periphery for two-way shear. If you look at the load transfer mechanism of this combined footing here, we have shear force diagram for this combined footing and also the bending moment diagram. You may generate this shear force diagram and bending moment diagram using the principle of statics by yourself also, or you can just model this simple footing by assuming them as slab and beam, and you can model this beam and slab combination in ETABS, and you may find the shear force diagram and bending moment diagram from ETABS also. So what we do is, I will just tell you a little. To find the longitudinal bending moment on any section, you have to do the sum of the anti-clockwise moment of each load to the left of this section. For example, if you want to find your bending moment here, then what you do is you find the sum of the bending moment to the left of this section for each load, and then you subtract the clockwise moment of the upward pressure between the section and the left hand side of the base, because you know that our uniform swell pressure is acting in this way along this whole slab also, and we have the factored column loads acting vertically below, and you can first find the reactions at both ends or at different support points that you consider, and after finding the reaction, take any section where you have to find the bending moment, find the summation of all anti-clockwise moments because of all the loads present along this left hand side of this section and subtract the sum of the clockwise moments that is generated due to the upward pressure from this swell, and by subtraction of these two clockwise and anti-clockwise moment you can find the bending moment at this section. And to find the shear force, what you do is you just perform the algebraic sum of the vertical forces on one side of the section. For example, if you want to find the shear force here, either perform the algebraic sum of the forces on this side or on the other side. So that is how you find shear force and bending moment diagram. So let's look here. We were talking about the critical section for one-way and two-way shear. The critical section for one-way shear is located at a distance of d from the column face. You can see the location here. This is the column face. And for two-way shear, it is at a distance of d by 2 from its column periphery. And if you look at this shear force and bending moment diagram, you can see here where we have the maximum negative moment. Remember, the moment is negative here, that is hogging moment. And here we have positive bending moment, that is sagging bending moment. And wherever we have the maximum bending moment, the shear force is 0. Also here we have maximum sagging bending moment, we have shear force 0, maximum sagging bending moment, shear force 0. So this is our shear force and bending moment diagram for these combined footings. And how we, if you remember that last point from our previous slide, what it says is that a simplified load transfer mechanism may be assumed. The footing is treated as a uniformly loaded wide longitudinal beam. So we treat this as a uniformly loaded wide longitudinal beam, and the loads coming onto these beams are the upward swell pressure from below and the factored column loads from the above. So considering that is the beam, we can draw the shear force and bending moment diagram. So the flexural reinforcement in the longitudinal direction is designed for the positive moment at the face of the column, reinforcement placed at the bottom, and maximum negative moment between the columns, reinforcement placed at the top. Okay, let's look here, and also let's go back to that diagram that I showed you. What you can see is that below these columns here, below these columns we have positive bending moment. That means if we consider this beam, the beam is bending downwards. So below these moments or below these columns here, we have to design for positive reinforcement, and this reinforcement will be located at the bottom face of our slab. Because the tension side is at the bottom, if we consider this as a beam, the tension side is at the bottom, so we design for positive steel, that is positive reinforcement for the slab under these two columns, whereas since we have a negative bending moment between these two columns, that means if we assume this as a beam, this whole combined footing slab is a beam, now our beam is deflected in upward direction, so that we have negative bending moment here. Now since the tension is in the upper side, for this whole middle portion we will design negative steel reinforcement, and that steel reinforcement will be placed at the top of our slab. You can go back to our diagram here and see that for this positive bending moment below these two columns, we have positive steel which is placed at the bottom of our slab, whereas for the negative moment between these two columns here, we have negative steel placed at the top of our slab. So the flexural reinforcement in the transverse direction in the column strip. This means flexural reinforcement in this direction. This is our longitudinal direction, but this is our transverse direction. We discussed that the transverse reinforcement is only considerate or is in considerable amount along these column strips. So these column strips we have selected the width is A1 plus 1.5D and A2 plus 1.5D. A1 and A2 are the size of our columns and D is the effective depth of the footing. So we have to place this transverse reinforcement only along the width of this column strip. It is not needed in this center portion or on these edges. The same is said here, I think. The flexural reinforcement in the transverse direction is designed for the positive moment at the section in line with the face of the column. Considering the column strip as a beam with uniformly distributed factored load. So this reinforcement is provided at the bottom and located in a layer above the longitudinal reinforcement. That means, let's look here, you can see here, if this long line is our longitudinal reinforcement, then this transverse reinforcement is placed at the top of this longitudinal reinforcement, and this transverse steel is also placed at the bottom section of our slab for the positive moment. So we will come to these things again while designing also. Just remember this load transfer mechanism and the shear force diagram, general shear force acting on these two column combined footing, and the bending moment diagram. I hope you have understood this. And finally, let's discuss now about beam slab combined footings. In our previous slide, we only looked at the combined slab of our two column combined footing. Here we will also see about the design of beams connecting these two columns. So in the case of relatively large footings, it is economical to design a beam slab footing. Instead of increasing the thickness of our slab of this combined footing, we can instead design for a beam connecting these two columns. So in the case of relatively large footing, it is economical to design a beam slab footing in which the footing consists of a base slab, similar to our previous slides, which is stiffened by means of a central longitudinal beam. Now this slab is stiffened by means of this central longitudinal beam, and this beam is interconnecting these two columns. The base slab behaves like a one-way slab, supported by the beam and bends transversely under the uniform swell pressure acting from below. The loads are transferred from the slabs are resisted by the longitudinal beam. The size of the beam is generally governed by one-way shear rate d from the face of the column or pedestal at a distance d. For effective load transfer, the width of the footing beam should be made equal to the column or pedestal width. The width of this beam is made equal to the width of our columns along this direction, and the high shear in the beam will usually call for heavy shear reinforcement. This is just some general information regarding beam slab combined footing. And the thickness of the slab should be checked for one-way shear rate d from the face of the beam. The flexural reinforcement in the slab is designed for the cantilever moment at the face of the beam and provided at the bottom. Two-way shear is not a design consideration in beam slab footing. Just remember this information. And the top and bottom reinforcement in the beam should conform to the longitudinal bending moment diagram, and development length requirements should be satisfied. So this was just some general information regarding beam slab combined footing. So this brings us to the end of our first lecture on this series, and today we just looked at some basic concepts of design of combined footing. In another lecture we will take one hypothetical example, or let's not say hypothetical. What we do is we model, analyze and design our building structure in ETABS, and after that we get the reactions coming onto our foundation from the ETABS model, and using those reactions we will design our combined footing also. But what we will do in our next lecture is, I have already designed, or I have one sample building whose design is analysis and design is complete. We will have some given values of the loads coming onto our foundation, and we will use the value of those loads and moments to design for combined footing. And in this lecture we will look at the design of an eccentric footing with strap beam. So we will first do or design that eccentric footing with strap beam manually, and then we will look at the design of the same in our CSI safe software also. So we will meet again soon with that design class. I want to end here for now. Thank you.